How y'all doing today? Alright, give me 1 minute. I'm finding a document I need. Go. Alright, so today we're going to be looking at our last bit of new material, which is over chapter 10. And we will review on Friday morning at 9 o'clock, 9 to 11. You don't have to watch it live. You can watch a recording. And I have a handout, or I have an upload, not a handout. Basically is my key to the review, so you're welcome to look through that as well. Okay. So, the last topic we need to cover is hypothesis testing. Maybe that's a little better. Alright. So the idea of hypothesis testing is a statistical hypothesis. I guess that's a better way to talk about it. This is a claim or statement about a population parameter, usually the mean, but we could also talk about proportion, which may or may not be true. Okay. And this is a hypothesis because we don't know if it's true or not. And the idea is, there's some established value that either some past research or past data supports, and we've collected new data that we think might show a different overall trend for the population being studied. For instance, if we have a research from 10 years ago that says that 10% of Mainland College population travels to the college through public transportation, which is usually a bus. But we take a survey of 100 students, and it turns out in that group of 100, we found 8 that use public transportation, which is 8%. Is that enough information to say that it's changed from the research that was done 10 years ago? It's now less than 10% instead of, maybe it's closer to 8%. We don't know for sure. But the idea is that we have new data that conflicts with old data, and we want to try to find a way to rectify that and test, is this new data within the realm of possibility, or is it actually telling us something different about what's going on with the overall population, and is it changing? Okay. So that's the kind of the basis of hypothesis testing and statistics. Anyway, so we usually start off with some kind of we're usually given a paragraph where we have some information being provided, and then we have to use that to set up our hypothesis test, and we go to and determine if it is enough information to claim that something has changed, or if it's not enough information. It's actually very similar to our confidence intervals in its own way. So it features a lot of the same things. We're gonna use the calculators to help us out quite a bit here, which is nice. Calculators will do a lot of the work for us, so that's good news. Anyway, so when we first start a hypothesis test, we identify 2 hypotheses. We have what's called the null hypothesis, and we have the alternative hypothesis. So one, the null hypothesis, which is denoted H with 0 as a subscript, which we'll call H naught. Naught being a more British word for 0. So the null hypothesis is a statement that establishes the currently accepted value for the parameter being studied. So we might say, for example, H naught establishes that the mean in something is equal to 0.86. Or we might say H naught tells us that the population proportion P is equal to 0.13. Usually it depends which one we're looking at, whether we're looking at a mean or we're looking at a proportion. This is what's already established as true from prior research, prior studies, prior data. Okay, this is what we're challenging. This is what we know to be true, and then our next statement is our challenge, basically. Our alternative hypothesis is the information that we want to put forth. Now, our alternative hypothesis which we'll call H1. This is a statement that describes how we think a parameter has changed based on our new research. That's all one word. A statement that describes how we think a parameter has changed based on new data. Now, in the previous page we said, for H0, H naught, the null hypothesis, we would say mu is equal to 0.86 or P is equal to 0.13. For our alternative hypothesis, we might say H1 mu we think is now greater than 0.86, or we might say H1 where the population proportion is now less than 0.13 or 13%. So notice that we use the original values here, but now we compare our result with the original value. So these values are the same as in H naught. And we're now saying, we're not saying that the mean is now 0.90. We're saying that, or our claim that we're making is that the mean is now greater than 0.86. We may have research that says the mean is 0.90, but we're not trying to establish a new standard. We're just challenging the old standard. It takes a lot more work to establish a new standard, but first step is to challenge or successfully challenge the old standard. So if we think we have enough data to say that the mean is now larger than 0.86, then that's what we can try to prove with our alternative hypothesis here. Okay, but we use the same value that we used in the null hypothesis, but now we say it's either greater than or less than. We could also use not equals. We're not going to worry about that here, but not equals is a little bit harder to prove. Anyway. Yeah, but these are our two examples. Okay. So that's the alternative hypothesis. Now, when we use the calculator, there's a couple of things that we would like to know. Let me get this last page here. First, we have the z-test, which as a hypothesis test for the mean when sigma is known. There we go. Notice that's some of the same issues that we had with confidence intervals. Whether we know what sigma is or we don't know what sigma is. We use what's called t-test, which is a hypothesis test for mu when sigma is unknown. We also have a proportion test, and this is a hypothesis test for P, which is the population proportion. Now, in the TI 83s and 84s, oops, there we go. We go stat, arrow over to tests. And we see right there, we have the first result is a z-test, the second result is a t-test, and for the proportion, it might be 5 here. Yes, that is correct. Okay. And then on the 36s, second stat. It's not a distribution. Are we able to do it with this? I don't know if we're able to do it this one. Nope. Let's see. I think there's a way, but use a distribution? No. You know what? I don't think we can do it on this one. Interesting. At least I don't see how. I don't think we can do these on the other calculator. Anyway, so it does work on the 83 and 84s. It does not work on 36s. So I might have to show you the old-fashioned way. It should do it on the 36s. We should go with that approach anyway. All right. So we can do it on the calculator. It is a little bit more work when it's a little more work when we don't have the calculator to do it for us, but we can get through it. All right. We may skip proportions just for the sake of time. Focus on the others. We'll see. Now, anyway, so we have errors that are possible here. Well, before we talk about errors, we should talk about conclusions that we would draw. So, in the conclusion of a hypothesis test, one of the following happens. Either we reject H naught, or 2, we fail to reject H naught. Notice that we never actually confirm our alternative hypothesis. All we're doing in a hypothesis test is deciding whether or not H naught is still a valid statistic or parameter. So either we reject it, which means we think it has actually changed and our alternative hypothesis is correct, or 2, we fail to reject it, which means we don't have enough information to say it actually has changed based on our results that we found. Now, so let me summarize there. Reject H naught. We have enough data to claim the parameter has changed. And if we fail to reject H naught, we do not have enough data to claim the parameter has changed as indicated. All right. Now, a type 1 error is rejecting H naught when H naught is actually true. Okay. The comparison we like to use here is that, type 1 error is like if we convict an innocent person of a crime. And then a type 2 error this is when we do not reject h0 when h1 is actually true. And the corresponding comparison we would make here is that we set a guilty person free. Okay. Which is worse? Well, it's hard to say because both of them are pretty bad for certain individuals or people around those individuals, depending on the scenario. We're not saying one is worse than the other, but both are problematic. And we would like for neither of those to happen. Now, we have what's called our level of significance. Which is the likelihood of making a type 1 error. Or the maximum probability of making a type 1 error. Okay. Typically, we use 0.01, 0.05, and 0.10 as our values here for this level of significance, which we used alpha to represent the level of significance. So we either use alpha equals 0.01, alpha equals 0.05, or alpha equals 0.10. Those are the ones we use most frequently. We could use others, of course, but that's what we use most often. Now, alpha equals 0.01, 0.05, or 0.10. This actually corresponds to 99% confidence, 95% confidence, and 90% confidence, respectively. With a higher level of confidence, there's less probability of making a type 1 error. But with a little bit lower level of confidence, there's a more chance of a type 1 error. Okay. So it's just whatever in the given scenario is considered an acceptable risk, I guess. How far apart can we, how to say that? It is a measure of risk, like how risky we do want our calculation to be, how likely are we to make an error based on that. So that's why we tend to use relatively low values such as these versus something crazy like 50%. We would never use 50% as a level of significance. It doesn't tell us anything. In rare cases, we could use 20% or 0.20, but even then, that's fairly it's a fairly large number to use for level of significance. So we prefer it to be one of these smaller values here. Anyway, but that's the connection with the confidence intervals that we had talked about previously. All right. Let's move forward and look at our classical approach to hypothesis testing. Step one, we always state the hypotheses, both the null hypothesis and the alternative hypothesis. So we state H0 and H1. Okay. All right. Next, we find the critical values from H1 and alpha. Okay. And at this point, we're really determining what kind of test we're doing. Thank you, tablet. If in H1 we say something is greater than, then we'll have what's called a right tail test. And if H1 is less than the parameter, then we'll call it a left-tailed test. Oops. Right-tailed test. And if H1 is less than the parameter, we use a left tail test. Now we say right tail or left tail. Here's our normal curve once again. Right tail means that we want Z, where the area is alpha. Okay. All right, and left tail is similar. That's not a great normal curve. Anyway, where we have a Z over here, and our area to the left is alpha. Okay. So depending on which comparison we're making, we can go in one way or the other. Okay, then we calculate a test statistic. Okay, so this really depends on what we're looking at. Well, we would use zt equals to x bar minus mu times square root of n over sigma. Okay. Basically, it's a calculation with z-score. It's an easier way to do this, I feel like. Anyway, I'm going to push through with this one. Finally, 4, we make a decision. We reject H naught if the test value is in the shaded region. Up here, depending on which scenario we're looking at. And we fail to reject H naught if ZT is not in the shaded region. Okay, and then finally we summarize the results. Now, let's talk about the critical values in number 2 here that we talked about. Our critical values, these are actually very similar to what we talked about in with confidence intervals when we looked at certain values there. Let's see if I bring it up real quick. I can figure it out pretty quick. Let's see. For alpha equals 0.01, z is plus or minus. Let me see. I lost it. .576. Alpha equals 0.05. Actually, you know what? I'm sorry, I made a mistake there. I'll just look it up. Alright. I'm using alpha, not alpha over 2. So I probably did it correctly the first time. I apologize for that, guys. I was just doubting myself. This first one's negative 2.33. Or either positive or negative 2.33. For 0.05, it's negative 1.645, or plus or minus 1.645. And for alpha equals 0.10, it should be 1. No, it shouldn't be. Let's see. I should just do it. 1.28. Oh, there it is. When I say plus or minus here, because it depends on which side it's on. If it's right tail, then it's positive. If it's left tail, then it's negative. Okay. Alright, I'm going to keep this page handy as we look at an example. Okay, close that. This is example 1. According to the American Time Use Survey, the typical American spends 154.8 minutes per day watching television. A survey of 50 internet users results in a mean time watching television per day of 128.7 minutes, with a standard deviation of 46.5 minutes. Conduct the appropriate test to determine if internet users spend less time watching televisions at an alpha equals 0.05 level of significance, and is there evidence to support the claim at alpha equals 0.05? And it says using the p-value method. Well, let's use the classical approach that we looked at instead. So let's write down some key values that we get from this first. This is according to the survey, so this is the nationally accepted value of the amount of time that a typical American spends per day watching American. This is mu. Survey of 50 internet users, that's N. And from this sample of 50 internet users, we got a mean of 128.7, that's X bar, and standard deviation of 46.5. We can use that as sigma. Okay. So just to write down our information first, let me get that out of the way. So we have mu is equal to 154.8 minutes. In a sample of 50 people, we had a mean, X bar, of 128.7 minutes. Our standard deviation is given as 46.5 minutes. And we want to do this hypothesis test at an alpha equals 0.05 level of significance. Okay. Here we are. So, first thing we want to do is state H0 and H1. Okay. Now, H0 always tells the population parameter, which in this case is mu. So let's say mu is equal to 154.8. Okay. Then we continue with our alternative hypothesis. Now, the important thing about the alternative hypothesis H1 is that we use the same value, 154.8, that we used in H0. The question is, do we think this is more than 154.8 or less than 154.8 based on our research? We look at our mean, X bar. From our sample of 50 people, we got a mean of 128.7. That is less than mu, so we suspect, based on this research, that our mean is actually less than this previous number that was established. That people are watching less television as more people start to use the internet. Although, if you think of it in terms of screen time, there's definitely been some shifts, probably in an increase, but anyway. But yeah, I mean, so that's what we're looking at. Here's the established value, and here's the value that we have found from our research, so we think this value is actually decreased. It's not that we're saying that the mean should be this number. We're saying that this number is smaller than this one, so we feel like this one is now too high. We think it should be less than that. Okay? And the likeliest outcome is that it is somewhere in between those two, if it turns out that we have enough evidence at this value. Okay? So we stated H0, we stated H1. Next thing we need is our critical values. So, since we're using mu is less than, this is a left tail test. Okay. So because alpha equals 0.05, that means z is going to be, we're going to use 1.645. Now, because it's a left tail though, we want it to be negative because we know 0 is right in the middle. Here's negative side, here's positive side. So in this case, z equals negative 1.645. So that's our critical value. All right, now we need our test statistic. So ZT is x bar minus mu times the square root of n over sigma. Now we have all of these values provided from the question itself. X bar is 128.7. Mu is 154.8. N is 50. And sigma is 46.5. Now, I think I gave you this formula before with n, square root of n in front. It could go either way. It doesn't really matter. So I probably should give it to you the opposite way. Anyhow. Alright, let's calculate this. So we want 128.7 minus 154.8 times the square root of 50, and then divided by 46.5. Well, that's awfully small. Negative 3.97. Okay. So now we make a decision. Going back to our instructions. So we have to determine if ZT, our test statistic, is in the shaded region. We reject H0 if ZT is in the shaded region, and we fail to reject if ZT is not in the shaded region. So Z, our critical point, is right here, negative 1.645. So our test statistic ZT is negative 3.97. Is that going to be to the left or to the right of Z? Left. So ZT will be over here, and it's negative 3.97. That is a 9. Okay. And so ZT is in the shaded region. So we reject H0 if ZT is in the shaded region. So we reject H0. So that is the decision that we ultimately make based on this hypothesis test. Now what that means, now we want to summarize the results. That means that we have sufficient data at the alpha equals 0.05 level of significance to say the mean amount of television watched has decreased. Okay. This statement that we make here is a lot like the statement that we made for our confidence interval problems. In this case, we either have sufficient data or we do not have enough sufficient data, depending on whether we reject H0 or not. We mention the level of significance, that's always important, and then we reference the problem, or specifically we're referencing the alternative hypothesis. Now our alternative hypothesis says that the mean is now less than 154.8. So our claim is that the mean amount of television watched has decreased. It's less than 154.8 minutes now. Let's do another one. We're going to find another problem ready to go. I don't know. I'll consult the book. Keep that handy. Okay. Get this out of the way. Yep. All right. Most of these are reject. Anyway. This is page 501, number 14. Do students who learned English and another language simultaneously score worse on the SAT critical reading exam than the general population of test takers? The mean score among all test takers on the SAT critical reading exam is 501. So that establishes the mean is 501. A random sample of 100 test takers, N is 100, who learned English and another language simultaneously had a mean SAT critical reading score of 485. So that's the mean for the sample, so it's X bar. And we know the standard deviation to be 116. So we want to test this at the alpha equals 0.1 level of significance. Okay. So that's the information that we need to get from the paragraph provided, or the sentence provided. We have the population mean, our sample size, our sample mean, the standard deviation, and the level of significance alpha. So we start off with H0, our null hypothesis. Our null hypothesis always state just the mean like it is. Mu equals 501. Now, based on our research here, do we think the mean for these particular students that we're interested in, do we think it's higher or lower than 501? Lower? Why would we say lower? Lower is correct. I'm just looking at the reasoning. Yeah, because we have a mean here, 485 from our sample. That's lower than 501. So we think mu is actually less than 501. Notice we use the 501 value in both cases. One's equal and the other is either greater than or less than based on this value. Okay. So critical point. We know this is a left tail because it's less than, and alpha equals 0.01, or sorry, 0.1. So we'll use z equals, we'll consult our paper here. So 0.1, or 0.10, we use z equals 1.28. Because its left tail be negative 1.28. So visually, this is what we're seeing. We have some z here, where a is our area to the left, and this is negative 1.28. Now we calculate our ZT, our test statistic. ZT, once again, is the square root of n times x bar minus mu divided by sigma. That's square root of 100. Yes, I made the same mistake, Daviana. 0.1 versus 0.01. Yeah. 485 is x bar. Minus 501, our mu, and then divide by our sigma, 116. And so now we calculate this value. And see that's 10 times negative 16 over 116. Let's just do that real quickly on the calculator. Square root of 100 times 485 minus 501. And then divide by 116. Okay. So that comes out to be about negative 1.38 right there. Okay. And so we look, okay, where in this graph is negative 1.38? Well, we know 0 is right here. This is the negative side, so negative 1.38 is actually in that shaded area to the left of our critical value z. So this is zt over here. So does that mean we should reject h naught or fail to reject h naught? Reject. Yeah. We reject h naught if zt is in the shaded region. Okay. And again, we want to finish that up with a sentence describing what this tells us. Now, it says, we have sufficient data at the alpha equals 0.1 level of significance tablet's at 5%. That's not good. I have to look to the right instead of ahead of me. Okay. Alpha equals 0.1 level of significance. That the what is this? This is the SAT test. That the SAT reading scores for students that learned English at the same time as another language is actually lower. Okay. I'll just turn that off. Okay. Alright, let me find one that's a right tail so we can look at that. Okay, yeah, there we go. This is problem 13 on page 501. The ACT is a college entrance exam. ACT has determined that a score of 22 on the mathematics portion of the ACT suggests that a student is ready for college level mathematics. So mu equals 22. To achieve this goal, ACT recommends that students take a core curriculum of math courses, Algebra 1, Algebra 2, and Geometry. Suppose a random sample of 200 students who completed this core set of courses in a results in a mean ACT math score of 22.6, and we have a standard deviation of 3.9. Do these results suggest that the students who complete the core curriculum are ready for college level mathematics? We want to use an alpha equals 0.05 level of significance. Okay. Now our null hypothesis, we just state the mu, which is 22. And for H1, are we going to say that mu is higher or lower than 22 based on our sample results? Greater, because we got an x bar that's higher than mu. Yeah, so we'll say mu is now greater than 22. It's not a lot greater, so that may not be enough information, but we'll see how it works out. That's our hypotheses right there, H naught and H1. Always want to state those first, but notice, I mean, we go ahead and jot down the key values like we did here, but then we immediately state the hypotheses. Next, we find the critical values. And notice again, this is greater than, so it's a right tail. So the critical value for alpha equals 0.05, we'll get z equals. Now, z is 1.645 plus or minus, but a right tail will be positive, so 1.645. Okay. Now, let's see. So we have a graph. Let's draw a graph. Okay, here's z, that's 1.645. Here's our right tail shaded in. Okay. Now we need a test statistic. So zt is square root of n times x bar minus mu over sigma. So it's square root 200 times 22.6 minus 22 divided by 3.9. So we'll take square root of 200 times parentheses 226 or 22.6 minus 22. That's pretty easy. Divided by 3.9. And we get a value of about 2.18 after we round. Okay, so the question is now, is ZT going to be in the shaded region, or is it not going to be in the shaded region? Well, 2.18, where does that lie in relation to our critical value Z? Yeah, it'll be in the shaded region because this is 1.645. And so it's going to have to be to the right of that. That's 2.18. So definitely bigger. Anyway. So does that mean we reject the null hypothesis, or do we fail to reject? Reject, once again. Like I said, most of these examples in the book are all reject. The one that has failed to reject is such a long problem, I didn't want to go through it. But yeah, so we fail. So we reject H naught. Now, if we fail to reject, the sentence that we write is not terribly different. That's strange. Okay. The Twitch didn't want to allow HO through as a term in the chat. So I had to allow it. Anyway, weird. Yeah, I guess I know why, but weird. Try writing H0 is not going to frustrate switch. Okay, so we reject H naught, so now we have to state what this actually means, and that is that, we do think, or we have sufficient evidence or sufficient data, is a better word, at an alpha equals 0.05 level of significance. Excuse me. It's a little cold in here. In this case, to say that the mean the mean ACT math score has increased, when students take the required classes or recommended classes. Which is really not surprising, but it's nice to be able to verify that scientifically, which is what we're doing. Okay. Every single one that we looked at here was reject, not fail to reject. If we fail to reject, then we would say we do not have sufficient evidence at an alpha equals 0.05 level of significance to say that the mean ACT math score has increased. The students complete the recommended classes. The only thing that changes is we either say we have or we do not have sufficient data. Okay. Otherwise, the rest of the sentence is the same. Okay. Now you'll have one of these on your exam, on your final exam, and you'll be expected to complete it and include a conclusive sentence. And if it doesn't go that well, it's not the end of the world. I probably will count this problem a little bit less because we kind of rushed through it at the end of the semester, so I apologize for that. But I want to give you a chance to see what you can do with it. So I spent today going over this material. Hopefully that has been helpful. Anyway, as I mentioned before, on Friday, 9 a.m. to 11, we're going to have a review session going over the final exam review for statistics that I posted over the break. So you can either show up and watch that live, or you can watch it recorded. You don't have to be there if you're not able to. But certainly if you can be there, it might be better than not, so you can ask questions specifically. And even after the meeting, I'd also have a set of solutions for the final exam review that I've written out, and I'll be sure to post those in Canvas also. So if you do have any questions, if I don't answer it during the class, hopefully you can look at my work that I've done and figure it out from there. I tried to be as descriptive as possible when I wrote these down. We'll see how it is. Now the Canvas conference? The Canvas conference is for your online test. Okay? So with the Canvas conference, um, basically, if you're online testing, when you go to test, you have to connect to the tester via conference, and basically you'll have to show like an ID card, like your school ID or your driver's license or something like that, just to prove your identity. Make sure you're the correct person that's supposed to be taking this test. And they'll probably check your calculator as well, which I've told them that we could use graphing calculators for this course, so it's not a concern. Um, anyway, so you will be supervised more or less, even though we're taking it online. You're expected to have a camera, a working microphone. So, oh yes, yes, I can do that. Um, yeah, I'll do that. Okay. Any other questions? All right. This is our last class, other than the review. So if I don't see you on Friday, then well, everyone, I wish you the best, both in this class, your other classes, and everywhere else beyond that. Next year, hopefully, we'll be back to more or less a normal schedule after everyone gets vaccinated, and we can be kind of sort of back to a normal life. So, um, anyway, if I don't talk to you again, have a good holiday and enjoy the time off. I know I will. And take care of yourself. So, alright. Well, you all have a good rest of the day. Take care. And I may or may not talk to you later. But please try to make it by Friday morning if you can. Alright. Have a good one. Bye.